Yeah, thanks very much for having me. I grew up in Southern California, so it's always a pleasure to be back. Um, so I'll tell you about a recent paper with Zohar Komargatzi and Fedor Popov. And maybe towards the latter half, I'll start to mention some ideas that are brewing with Mitchell Choi. That's work in progress. The basic spirit of the talk is going to be to try to sort of use various techniques in quantum field theory, some of them a little bit more familiar, like the irreversibility of the renormalization group flow and symmetries and anomalies, some of them maybe less, like higher vary phases, to try to learn new things about defects in quantum field theory. And so, okay, so I should start by saying, what is a defect? A defect is simply modification of a quantum field theory that you do along some kind of locus of space-time. And when phrased in this way, of course, we've all studied examples of defects, namely local operators. These are sort of the first defects that we learned in quantum field theory classes. But there's nothing that obstructs us from also considering defects of higher dimension, such as lines, surfaces, membranes, and so on. And so the question is, why would we be interested in studying such extended objects? I think probably the sort of first answer people will tend to give you is just that they have tons and tons of killer applications. For example, if you're a high energy theorist, you might be interested in Wilson or 't Hooft lines because they're useful for diagnosing phases of gauge theories. If you're a condensed matter theorist, then, for example, line defects are potentially useful in modeling impurities in some kind of material that you're interested in studying. Recently, there's been a kind of renaissance in our understanding of symmetry in quantum field theory. And in particular, we now sort of understand that the sort of subset of defects that are in particular that behave topologically in correlation functions should be thought of as kind of generating some kind of generalized notion of symmetry. And if we're charitable and include things like boundary conditions under the umbrella of extended objects, then the applications just proliferate from there. For example, everything from branes and string theory to finite size effects, and so on and so forth. But I think there's a more basic reason to be interested in defects, which is simply that they're part of the defining data of quantum field theory. And so if we're interested in understanding what quantum field theory is, then these are the kinds of things that we should, in principle, be able to contend with. Okay, so that's, I guess, the why. And this is the what. So what in principle are we interested in learning about defects? So in this talk, I'm mainly going to be interested in sort of very coarse questions. And they sort of take the following shape. So a very common question that we ask in quantum field theory is we sort of fix the system in the UV and maybe perturb it by some relevant deformation and ask what we get at long distances. And there's a kind of defect version of this general class of question as well. So we fix some theory in the UV, which I'm going to take to be a conformal field theory. And you specify some defect. And let's suppose it's a two-dimensional defect. And we sort of perturb the system by a relevant operator that is integrated along just the locus of the defect. So if you like, we add something in the schematic form. an integral over O to Lagrangian. And since we're only perturbing the defect, nothing happens to the bulk theory. But in principle, we trigger some flow to some new defect at long distances. And the question is to try to identify what the physics of this defect is, at least at a very coarse level. So, as I said, I'm not going to be interested in answering particularly detailed questions about what DIR is, but rather I'm mainly going to be interested in differentiating between the following possible IR scenarios. So, and let's, just for simplicity, I'm going to, from now on, stick to the special case of p equals 1, which describes line defects. Although much of what I say in this talk, you can imagine, has higher dimensional avatars as well. So, okay, the most boring scenario is that you, and maybe in some sense generic, is that you do this deformation and the line defect flows in the IR to a completely trivial defect. And sometimes people sort of write this as the line defect has flown to the identity operator at long distances. And in words, we'll call this trivial. So in this scenario, an observer that's situated at long distances, if you like, away from the locus of the line, sort of can't really do any long distance load of the experiment to see that the defect is even there. Another possible scenario is that the line defect just completely decouples from the bulk. And in this case, there can still be something slightly non-trivial about it. Namely, you could have sort of some number of super selection sectors, say n of them. And, or if you'd like, you can alternatively say that the defect has flown to a decoupled topological quantum mechanics, some decoupled 0 plus 1D theory that is just the theory of n ground states of identical energy. So sometimes I'll call this TQMN or decoupled. Another scenario is that the line can become topological at long distances. So in this case, it would generate some kind of emergent higher form symmetry, or maybe even a higher form symmetry that was there in the UV already. And the last scenario, which is maybe in some sense encapsulates all the others, is that it could become non-trivially conformal at long distances. Okay, so this is a kind of menu of different possibilities, and we want to figure out in examples which are realized.
I guess you're assuming the line is not charged under a one-form symmetry.
Yeah, I will be assuming that, or alternatively, yeah, you could say that if it is charged under a one-form symmetry, then you rule out maybe the first option, I guess, that you can't float to the trivial line or something. Maybe also the decoupled option. Yeah. So yeah, right. But indeed, the examples that I'm going to talk about will all be in the absence of one-form symmetries. Okay. So, okay, so now we get to the how. And as I said, I'm going to mainly focus on using these three techniques sort of in combination, and I'll do them sort of one at a time, and at the end, hopefully I'll be able to get to one example, namely the spin-flux duality that kind of uses them all together in some sense. Okay, so let's start with the irreversibility of the renormalization group flow. So maybe the first example of this that one sees is the C theorem. So this applies to 2D unitary CFTs. There's some quantity called the central charge that you can compute in a conformal field theory. Operationally, it's sort of it appears in the 2-point function of the stress tensor. Actually, it appears in a million different places, but in particular, this is the maybe most straightforward way to diagnose it. And the C theorem says that if you have an RG flow from a UV CFT to an IR CFT, then this central charge basically decreases. And this is very useful for constraining RG flows. For example, it rules out infinitely many possibilities right away for what the IR theory could be. And there are, by now, a variety of generalizations of the C theorem that apply in all kinds of dimensions and with defects of arbitrary codimensions. The one that is going to be relevant for us is the G theorem, which applies to line defects. And it takes the same sort of schematic form. It says there's some quantity that you can associate to line defects that decreases under just situations where you perturb the line. I'm not allowing for sort of simultaneous flows of the bulk and the defect. And what is this quantity G? Roughly, it's what it wants to be is the expectation value of a loop of the operator. This has some mild scheme dependence, which you can eliminate by essentially, sorry, it should be on the, sorry, that you can eliminate by acting with this operator here. Okay, but basically it's the expectation value of the line in a loop. Okay, and so.
Is it also the same as the coefficient of the Coulomb potential?
That's a good question. I'm not sure actually. I didn't think so, but
Then it could for conformal line defect. Coulomb potential has to be Coulombic, right? Dealing with R is fixed, and then there's a dimensionless coefficient.
Right. It's like the finite part of the expectation value of the line in a loop.
With the circular loop,
Yeah, circular loop, right.
That the Coulomb potential is defined through a rectangular.
Rectangular, yeah. I'm not sure how to extract it from the rectangular. Yeah, rectangular loop. Good. So it'll be helpful to go through each of these 4 different possibilities and say what the G function could be. So in the case of a trivial line defect, you're essentially just computing the thermal partition function of a trivial quantum mechanics theory. So the G function is basically just 1. By similar logic, if you have a decoupled topological quantum mechanics, the S1 partition function is basically just calculating the number of ground states. And so you get that G is a positive integer. So if the line is topological, then G is sometimes called the quantum dimension. And it's known basically from this generalized symmetries community that it can basically be any, well, there might be some kind of like algebraic constraints on what the number can be, but roughly you should think it's kind of a real number that's greater than or equal to 1. And in the most general case that it's a conformal line operator, then the most that you can say is that it has to be greater than 0. Okay, so let me give you an example of how G theorem can be used to constrain defect RG flows. So there's a general class of defects that are called pinning fields. And the way that they're defined is you sort of fix a bulk bulk CFT, which has an operator O of dimension less than 1. So it's relevant from the point of view of line defect RG flows. And you basically define a defect by taking the action of the CFT and kind of deforming by this relevant operator. Okay, and if you like, you can think about this as a kind of flow from the UV, where the defect in the UV is basically just the trivial defect, and therefore has G function equal to 1, down to the IR. Now we ask what could we possibly get? And the G theorem essentially immediately rules out a bunch of possibilities. So for example, it's a strict inequality, and therefore it immediately tells you that, well, G equals 1 is ruled out because GUV was 1. Similarly, the decoupled scenario is ruled out, and also the scenario where it becomes topological in the IR is also ruled out. And the only possibility is that it basically becomes a conformal line defect at long distances. Sorry, is this too low, by the way? Well, right there again.
What does G equals 0 mean?
G equals 0. Yeah,
Because this is like much stronger than the C theorem, right? So something here is the C theorem doesn't tell you that you have to have a CFT. It says if you have two CFTs, then one is okay. But now you're telling me something much stronger.
yeah, that's right. It is an interesting peculiarity of line defect RG flows that G theorem alone can kind of guarantee conformal.
So what does G equals 0?
But for example, like if you tried to do this for surfaces, you would run into the same problem that the B theorem kind of isn't as strong as the G theorem. It can't really like tell you that it has to be
Because it's gone below. What stops you from?
basically because for example, if you try to do the spinning field argument, like B equals 0 can be saturated by like a TQFT or something, or like so yeah. I agree with you that G for some reason is more powerful in that sense than C theorem. But you were asking G equals 0. Why
Yeah,
G equals 0?
G equals 1 converted to G equals 0, and that sounds like something that should be also considered trivial in whatever sense.
Let me say that it's believed that like healthy RG flows don't ever get to G equals 0. G equals 0 is sometimes called like a runaway RG flow. It's the only example that I know of where this happens is in free theory. As a free theory example where you can think about it, I suppose, as the well, really it's that the RG flow kind of never ends, but if you like, you can think about it as GIR is like 0. Then yeah, for some reason, yeah, I don't know how to describe that in this language. Good. Any other questions? Okay. Yeah, so the upshot is that barring this kind of exotic runaway scenario, pitting field defects are generically expected to be conformal at long distances. Okay. So that's the G theorem, and next I want to tell you about how to use symmetries and anomalies. And there's very closely related work that was done here that a lot of the discussion that we're going to have will have overlap with. So one of the ways that symmetries are useful in quantum field theory is through their anomalies. Basically, anomalies are these robust kind of quantities that you can associate with a symmetry acting on a quantum field theory, and they're the idea is that you can compute them in the UV and they're sort of preserved along the entire RG flow. And they exclude various possibilities simply because, for example, a trivial endpoint is incompatible with the UV having an anomaly. So let me try to tell you about the kinds of anomalies that I want to discuss. So the setup is, let's now specialize to 2 plus 1D just so I can draw pictures a little bit more easily. And assume that the bulk has some just standard zero form symmetry group. I want to be able to use this symmetry to constrain line defects, so I should put in some kind of assumption that my line defect preserves the symmetry. And one definition is you want that, so good, so here's my line defect. And part of this renaissance that I was telling you about earlier, whereby we understand symmetries as corresponding to topological operators, is that whenever you have a zero form symmetry, that means that you have some codimension one topological defect that implements the symmetry. So that in particular means that for each element of the group, I have some surface operator, since we're in 2+1 dimensions. So I'll write little g to label the surface operator. And the requirement that the line defect preserve the G symmetry amounts to the requirement that when you take a sort of cylinder of this topological surface and you collapse it on the line, then you should get the same line defect that you started with back. Okay. If you'd like, this in particular implies that all of the G surfaces admit a topological point junction with this line defect that I want to study. You can sort of go from this picture to that picture by kind of squeezing the top and flaring out the bottom, and then you kind of get a picture that looks like this.
Does it go both ways, or?
Yeah, it's basically. Good, but I'm going to mainly use this presentation. Namely, I'm going to use the existence of these topological point junctions, X. And I want to define a notion of a defect hoofed anomaly. And so I want to emphasize that this is different than the symmetry in the bulk having an anomaly. So in particular, in all the examples that I'm going to discuss, the bulk theory, the G symmetry acts completely non-anomalously in the bulk, but it's sort of a contribution to the anomaly that comes purely from the fact that I'm inserting a defect. And this is how it's defined. So what I do is I take my line defect and I try to fuse two symmetry surfaces. In the presence of this line defect. And when I do this, so I had to fix some choice of these junctions in advance. Your choice might not be the same as mine. In particular, you could have defined yours to be rescaled compared to mine by some phase. But I fixed them in advance. And when I do this fusion, I'll get back the sort of surface associated to G times H, and I won't in general be guaranteed to get back the same junction that I chose in advance, but I will be guaranteed to get it back up to some phase omega.
Are you assuming that the junction, the space of junctions is one dimensional?
Yeah, that's right. I am assuming that indeed.
Is there some generalization of that?
Let's see. Yeah, I want to say that if you don't assume that, it's sort of like assuming non-simplicity of the line,
But if you assume the line is invariant under G, then seems like you can treat them each separately.
Although
And then you just always have a one-dimensional junction space.
well, yeah. I mean, if the line was non-simple, then it itself would have its own topological junctions, and I could sort of fuse them onto this one, and I would get a higher dimensional space. But yeah, I think basically if you assume that the line itself is simple, then they're always going to be one-dimensional spaces. Good, thanks for the question. So these phases omega are not totally arbitrary. For example, the fact that if I took three three of these surface defects and fuse them together in different orders, I should get the same result. That if you chase the diagram and write out what it means at the level of this omega, then what you'll find is that associativity of fusion implies that omega is a true cocycle. And as I said before, this choice of junction was sort of arbitrary up to some C number rescaling. So if you went and computed your omega prime using these slightly different choices of junctions, then what you would find is that your omega is related to mine essentially by an exact 2 cocycle. So something like this. And the math problem of sort of calculating 2 cocycles modulo this equivalence relation that two cocycles are the same if they're related by an exact 2 cocycle is precisely the problem of group cohomology. And so we learned that the physical information about these phases is some class in the second group cohomology. And this is the thing that we want to call the Clift anomaly.
Is it known that there are no beyond cohomology anomalies?
Well, so it sort of depends on what you mean. So as you go up higher in codimension, so as your bulk becomes higher dimensional, you can get new kinds of anomalies that kind of play with the normal directions to the line defect. But I'm not going to be considering those. I'm basically just going to be considering this class of anomalies. And I don't think there's any beyond.
Because that also classifies like anomalies for one-dimensional theory, right?
Yeah,
But
exactly.
if the theory is fermionic, that's incomplete, right? There's like H1 class as well.
I will be assuming bosonic line defects throughout. Yeah.
But like for fermionic theories, there might be also a beyond cohomology anomaly.
Yeah, so I would say in general, you sort of at least have, so for p-dimensional defects, you at least have the anomalies that p-dimensional quantum field theories can realize. And then you have some more generally coming from normal stuff, funny stuff that happens with that plays with the normal directions. But so
I would say that it's probably usually much bigger than that, or at least bigger than that. Because for if it's not bosonic, if it's fermionic, it should be bigger than that.
If it's fermionic, it might be bigger than this, yeah. I hadn't thought about fermionic line defects, but yeah, principle.
Are you talking about fermionic line defects or fermionic field?
Fermionic line defects would be enough, I think.
In bosonic.
In
So for example, omega could be W2. You could have a bosonic theory in which omega is W2.
So that's an example where this is one of these anomalies that plays with the normal direction.
You could think of it like that using a junction.
That's right. So I'm not going to be considering lines which have this W anomaly. Yeah. Good. Okay. So this is the definition. What are the consequences? So one fact is that if we look at the Hilbert space of endpoint operators of this line defect, HD, then these operators transform projectively under the G symmetry. So HD is in a projective representation. The different sort of flavors of projective representations of a group G are precisely labeled by 2 cocycles, and that 2 cocycle indeed labels what kind of projective representation you get, corresponding to omega. So in particular, for example, if this 2 cocycle is non-trivial, then from the fact that a group has no one-dimensional projective representations, you automatically see that there's going to be degeneracies over the space of endpoint operators. And two, you have the usual nice stuff that you get whenever you have anomalies, namely, they have to be matched under RG and across dualities. And so, in particular, if this 2 cycle is non-trivial, then the defect in the IR cannot be trivial either. Because a trivial defect has trivial 2 cycle. Okay. And let's do an example. So let me take, I'm going to fix my bulk to be the O2 model in 3 dimensions. And I want to tune the potential so that I'm sitting at the critical point. And for my defect, I want to take what's sometimes called a spin impurity. So in a sense, I want to couple the bulk to some, at first, decoupled quantum mechanics, like a qubit supported on the on a line. And so the way I do that is I take for my action the bulk action plus the action of a quantum mechanical spin S particle. Plus I add the following term. So I want to do this coupling in a way that preserves the O2 symmetry. And if I'm remembering correctly, I should do it like this. A little more carefully. I'm going to put it at the origin of space. Okay. So maybe it'll be helpful if I say what this this action is. So it's not commonly taught in quantum mechanics classes, but turns out there's a completely Lagrangian way to describe a qubit with 2s plus 1 states. Sometimes it's called the cojoint orbit method. So the way you do this is you take a quantum mechanical theory with the following field content. So I'll have a tuple of complex scalar fields and also a U1 gauge field. And take the following as my action. So here I basically have a first order action in these Z's, and there's some U2 symmetry that rotates these Z's around, and I gauge one of the U1s sitting inside of it using this this gauge field lambda. And I add a 1D transimmence term.
So the pi,
Sorry?
what is the coefficient?
2s.
Is that pi in front of the?
Yeah. Sorry. So 2s is an integer.
Mhm.
And if you could just go through the more or less elementary exercise of quantizing this theory, and then you'll find that indeed it has 2s plus 1 states, and the SU2 symmetry is implemented by the following operators. Well, yeah.
Just the CP1, right?
Yeah, exactly. Okay. Good. And so these S plus and S minus are just you know, Sx plus I, Sy, plus or minus Ix, Sy. Good. So these are sometimes called spin impurities because it's like I'm coupling some kind of spin impurity to my bulk O2 model. And again, we can ask the same flavor of question that we've been asking, which is what does this flow to at long distances?
Energy is preserved.
Sorry?
The O2 is preserved or broken?
Yes, O2 is preserved, indeed.
Is there a trace interaction?
Sorry?
In the interaction, is there a trace or
No,
S plus and minus, are they not matrices?
they're not matrices.
Oh no, yeah, you're right. So
yeah, they're not matrices.
the symmetry is SO3, it's not SU2, right?
Yes, exactly. That, yeah, so that'll be crucial actually in what follows. Good. So the way you can think about this is you have in the UV,
This thing has time reversal too, though.
it also has time reversal. For simplicity, I was going to ignore time reversal in what follows and just look at purely internal symmetries. But in the paper, we actually did also analyze the anomaly of the full C2 time reversal times O2. Good. So indeed, you can think about this as starting with the O2 model in the UV plus a decoupled spin S particle. And then adding this interaction, and then asking what you flow to in IR. And so because in the UV, it's basically bulk CFD plus a decoupled quantum mechanics problem, the computation of the anomaly is very easy. So this thing that I was calling the defect Tooft anomaly is basically just the ordinary Tooft anomaly in the sense of quantum mechanics of this qubit. So for example, let's forget for a moment about the fact that actually just the O2 symmetry is preserved and think about the anomaly of the full SO3 in just this decoupled quantum mechanics. And as was pointed out, the symmetry is actually SO3, not SU2. One way to see this is to note that the center of SU2 can sort of be undone by a gauge transformation. Alternatively, if you look at the local operators of the theory, the only SO3 acts faithfully, not the full SU2. And usually you define the symmetry to be the thing that acts faithfully on local operators. Yet we know that the states in this theory, there's two S plus one states, they transform in the spin S representation of SU2. And that, when thought of as a representation of SO3, is projective if S is a half integer. So if S is in 1/2 plus Z, then there's a Tooft anomaly. Corresponding to the non-trivial element of H2 of SO3. While if S is an integer, then there's no Tooft anomaly. So immediately you learn that when S is a half integer, the spin impurity has to become non-trivial in the IR. Actually, sorry, so I have to say one more thing, which is that, so this is the anomaly of SO3. The O2 symmetry that's preserved by the setup is a subgroup of this SO3. But the anomaly of that subgroup is completely fixed by the anomaly of the SO3 by pulling it back along the inclusion. And you can just do the exercise of checking that indeed that O2 subgroup is anomalous, sort of if and only if the SO3 that it's sitting inside of is anomalous. So this analysis that we did for this SO3 carries over sort of identically to O2. Okay. So this conclusion wasn't as strong as the one that we were able to have for pinning field defects, because although the defect has to be non-trivial, a priori it could still be decoupled or topological or conformal, and so it'd be nice to be able to say a little bit more. And in the special case that S equals 1/2, then we can say a little bit more using the G theorem again. So when S equals 1/2, GUV is equal to 2 because it's a decoupled topological quantum mechanics in the UV with two ground states. From our earlier comments, G is the number of ground states. And well, so we know that GIR has to be less than 2. So what could it be? Let's rule out the possibility that it could be decoupled. So if it were decoupled, either it would have to be the trivial defect, which we just ruled out by the anomaly, or GIR would have to be an integer. Let's say greater than or equal to 2 if it's non-trivial. And on the other hand, the G theorem tells us that GIR is less than 2. So immediately, that means that the defect is not decoupled. Actually interacts in a non-trivial way with the bulk. And there's one more thing we can say, which is that in the O2 model, it's believed that there are no one-form symmetries, which in particular means that it's believed that there's no topological line operators for this defect to flow to either. And so therefore, no topological ones in O2 model implies that DIR can't be topological either. And so the only possibility that's left is that, in fact, this S equals 1/2 spin impurity becomes conformal, a non-trivial conformal line operator.
What is the evidence for that belief?
That there's no one-form symmetries. Basically, I don't think there's any evidence. It's more like if there was a one-form symmetry, presumably we'd be able to write down lines that are charged under it, and I just don't think anybody's ever managed to write down, for example, non-endable lines. So yeah, I would say the evidence is not great because I don't know, there could be some non-invertible one-form symmetries, and it's generally quite hard to say when we've sort of exhausted the full sort of like list of topological defects that a theory has. But this is at least the belief. There's some no topological lines in O2.
Why always decrease?
Sorry?
Why that G always has to decrease?
That's the statement of the G theorem. So G theorem is a strict inequality as long as there's actually a flow. Thanks for the question. Okay, so good. Okay, I want to tell you about one more thing.
Check numerically.
Good. Yeah, so this defect sometimes called the halon. And yeah, indeed, people have done lattice simulations of this defect, and they do observe that it looks like it behaves conformally. So yeah, so certainly this claim is not ours, but maybe this is a kind of argument that high energy people can sink their teeth into.
What about higher S on the lattice?
Good. So it's actually believed that every S defines a conformal line operator. This has been checked for S equals 1. And I don't know of any arguments that like get you all the way to conformal for higher S, but there are different things you can say that are compatible with that. For example, this next kind of anomaly that I'm going to tell you about, an anomaly in the space of coupling constants, would be compatible with that, though it doesn't quite.
Or for
fit.
integer S.
Sorry,
You're-
also for integer S, yeah.
Is there some large S analysis?
Ah, yeah, sorry, I should also say that Zohar and Gabriel and others, Mark Mazet, I think, bless you, did indeed do a large S analysis of the O2 model, and they find that for S large enough, it gives conformity as well. So somehow, yeah. The fact that large S is conformal and S equals 1/2 is conformal might embolden you to conjecture that it's conformal for all S. Good. So the last technique I want to tell you about is what is sometimes called anomalies in the space of coupling constants. And the basic idea is you sort of soup up the setup that we've been considering so far by, in addition to having a G symmetry and a defect, having actually an entire family of defects, maybe labeled by some parameter space X, or call it M, I guess, sorry, parameter space M. In principle, you could take this parameter space to be very general, but actually I'm going to, and without loss of real generality, specialize it to be S1. And the reason is because the kind of anomaly that I'm going to tell you about when computed for a general parameter space amounts to sort of computing it for all the one cycles of the parameter space. So you kind of can reduce the computation of the anomaly in the most general case to the computation of the anomaly in the case of S1. And okay, so the basic idea is that you should think of this kind of anomaly as a kind of mixed anomaly between the topology of the parameter space and this G symmetry that we're assuming that we're preserving. And I'll call this theta, just because theta is a 2π periodic variable now. And so there's a variety of ways that you can define this anomaly. I'm going to give you a kind of a definition that I think is going to be the most easily generalized to a variety of settings. It's inspired by the fact that anomalies form a spectrum in the sense of algebraic topology, but if those words mean nothing to you, then don't worry about it. So the basic idea is the following. So we have our line defect, and what we're going to do is we're going to allow, so we have some family of line defects, but we're going to allow this parameter theta to vary as a function of time. So we're going to give this theta parameter a profile along the line. And in particular, the profile that I want to give it is a profile where, so this is tau, this is theta tau, is a profile where it very rapidly jumps from 0 to 2π at t equals 0. And if you like, sort of in the limit that this happens basically instantaneously, then what you can think you've done is you've defined a local operator, which I'll call P, because it's closely related to pumping in the sense of Alice pumps. This defines some local operator P on the defect defined by, theta equals 0. Okay. And now we have this local operator supported on this line defect. We can interrogate what its charge is under the bulk G symmetry. So for example, we can take our G symmetry surfaces and encircle P, this pumping operator, with them. And when we do this, we will get some phases. And we can interpret these phases as defining an element of H1 of G with coefficients in 1. Okay, and this is what I'm going to take as my definition of the anomaly of the S1 family of lines. Okay. And so maybe it will be helpful to do it in an example. I'll also maybe explain how to diagnose the anomaly in sort of more conventional way. So let's take as our model in the bulk the abelian Higgs model. So it's a theory of a U1 gauge field plus a charge 1 complex scalar. And again, we want to tune the bulk so that it's sitting at the critical point. The family of defects that I want to consider are sometimes called vortex lines. So they're defined in a sort of funny way. They're defined in the way that disorder operators are defined. So they're not constructed out of fundamental fields of the Lagrangian, but rather they're sort of implicitly defined by modifying how we do the path integral so that we only integrate over field configurations that have certain singular boundary conditions as we approach the locus of the defect. And so in particular, in this case, the way that we're going to define this vortex line V alpha is we're going to demand that as you take the holonomy of the bulk gauge field along very tiny loop C that link the locus of the vortex line, we want to demand that we're only doing the path integral over field configurations that have some fixed holonomy alpha. And because alpha is a holonomy, it's a 2 pi periodic parameter, and therefore this defines an S1 family of line defects in the abelian Higgs model. Now, maybe let me, for comparison, just briefly explain the kind of usual way people would talk about detecting an anomaly in the space of coupling constants. So one thing that people commonly do is they couple the theory to a background gauge field for the symmetry that's being preserved. So in this case, I didn't say, but there's two facts that are going to be important. One is that there's a parameter space, but also there's a U1 symmetry that's preserved by these line defects, sometimes called the magnetic symmetry, that exists in any 3D abelian gauge theory that doesn't have dynamical monopoles. And I don't have time to explain why these line defects preserve the symmetry, but they do. And actually, I have so much little time. So actually, let me just tell you what the answer is. So what is the pumping operator that you get when you sort of quickly pump these vortex lines from 0 to 2 pi? The pumping operator that you get, in fact, turns out to be precisely a magnetic monopole. And magnetic monopoles are exactly the local operators in 3D U1 gauge theories that carry charge under this magnetic U1 symmetry. And so in particular, this pumping operator has charge 1.
So it can leave the line.
Sorry?
It
can leave the line, yeah. Exactly. Has charge 1. And therefore, this is a kind of signature of the fact that there's an anomaly in the space of coupling constants. And the implications are that, well, one implication that is maybe the most interesting is that these vortex lines, there should be some special value of alpha such that the vortex line becomes non-trivial. And the claim is going to be that this happens at alpha equals pi. And in fact, the conjecture is that it defines a conformal line defect. And let me conclude by telling you why we think that conjecture is true. And the reason we believe that conjecture is true is because it would be a corollary of an even stronger conjecture, which is the spin-flux duality conjecture. So in the bulk, the abelian Higgs model enjoys a beautiful duality with the previous example I discussed, which is this O2 model. Particle vortex duality. And you can in particular ask what these vortex lines map to under particle vortex duality. And our claim is that the pi flux vortex line precisely maps to this S equals 1/2 spin impurity that we defined earlier for the O2 model. And if you recall, the conclusion was that this line is conformal, and so in particular, I would follow that this is conformal. You could ask, what does a more general vortex line with a more general holonomy map to? And the answer is that this sort of corresponds to deforming the action by basically a poly Z. And gamma. This one? Sorry. Writing's terrible. So this would be a special case of this. So yeah, so when delta alpha equals 0, then gamma equals 0. So in a sense, deformations of the holonomy map to this gamma parameter. And okay, as with all of these sort of strongly coupled IR dualities, you can't really, it's difficult to prove them. So the only thing you can do is say what evidence you have, and there's a kind of standard list of things that you check. And let me just conclude by telling you the list of things we checked. So the first thing is that the symmetries match. So when the holonomy is pi and when gamma is 0, then both line defects preserve the full bulk O2 symmetry. When you turn on this gamma parameter, or when you turn on a non-trivial holonomy, then you break the O2 down to a U1. So that's the first check. The second check is that when you turn off gamma and delta alpha, and you're sitting at this more symmetric point, then you can calculate these standard defect Hooft anomalies that I was discussing earlier, and they match. So they both have the same O2 defect Hooft anomalies. At delta alpha equals gamma equals 0. So for example, the endpoints of this vortex line transform like a doublet of so-called half monopoles. So that's the projective representation that determines the Hooft anomaly of this vortex line. The anomalies in the space of defect couplings match. So that sort of gives evidence not just for this identification of the pi flux vortex line with symmetric spin impurity, but further for the entire family of vortex lines with this entire family of spin impurities. And the other thing that you can check is that the defects sort of agree when you deform the bulk by mass terms. So let me just quickly draw the phase diagram for what that looks like, and then I'll conclude. So, so if we're in the O2 model, in the bulk, we have some conformal fixed point here. And if we turn on a mass squared, then we trivially gap the theory. And if we turn on a negative mass squared, then we spontaneously break the U1. And the claim is that if you take this S equals 1/2 spin impurity, then we sort of argued that it's conformal at the fixed point. In the trivially gapped phase, it becomes a decoupled qubit, as you might imagine, because the trivially gapped theory doesn't have that many lines. And in the spontaneous symmetry breaking phase, it actually flows to a Z2 subgroup of the emergent U1 winding symmetry that Goldstone bosons have in 2+1 dimensions. And if you do the same analysis on the abelian Higgs side, then you find in these two massive phases, you get the exact same answer. That in the pre-maximal phase of the abelian Higgs model, you flow to the Z2 form electric symmetry line. And in the sort of Higgs phase of the abelian Higgs model, you flow to decoupled topological quantum mechanics. Okay, so that's basically all I had to say. Thank you.
In the Higgs phase of the abelian Higgs model, like where are the 2 degrees of freedom coming from for the pi vortex?
Yeah, so the way that we did this is we basically solved the like ANO vortex equations, but with funny boundary conditions at the origin that reflect the fact that there's a vortex line inserted.
Mm-hmm.
And so if you solve it with these funny boundary conditions where you force the holonomy at the origin to be
there's
pi, then there's 2 degenerate solutions that kind of like look like this. And they're exchanged by charge conjugation. And so we kind of use this semi-classical kind of argument for the 2.
okay. And this is supposed to be an IR duality, like the G function for the pi vortex might be like 7 or I mean whatever. So it could be something larger than 2.
Yeah, so if you just use the abelian Higgs side, I don't know how to constrain G for this pi flux line, but if you believe this duality, then it has to be between it has to be less than 2 because because if we apply G theorem here, this can be constructed from a UV defect that has G equals 2.
Yeah.
So its G is less than 2, and I think there's a lower bound also. I think it.
But there's no reason
Why
that
should it be
GUV on the left side should be less than the GUV on the right side.
Oh no, GUV doesn't have to be, but the pi flux vortex line itself and the IR line that it flows
Oh
to
yeah, sure.
would have to have at least G less than 2, let's say, and G greater than 0.
Can I ask, in the O2 side, you have infinite many conformal lines just by changing X.
Yeah.
Do you know what happens on the other side?
Right. So good. So one stupid thing I could have said in advance is, this is defined as a spin impurity that's coupled to the bulk phi field. You can map that across particle vortex duality. The particle maps to a vortex. So you could write down the same thing that you wrote on this side, except you would couple the spin impurity to a monopole operator of the bulk abelian Higgs model. And that should, in some sense, be the answer for all S. And if you'd like a different way of saying what this spin-flux duality conjecture is that in the special case that S equals 1/2, that spin impurity coupled to a monopole operator enjoys an IR duality with this vortex line description.
Could you repeat that? I'm sorry.
Yeah, so sorry, good. So I'm just saying, so we had this expression where we wrote something like this kind of coupling. This is like how it couples to the bulk, the spin impurity on the O2 side. I'm just saying that like a stupid thing you could have said is, under the particle vortex dictionary, the phi field maps to the monopole operator of the abelian Higgs model. And so you could have written down a abelian Higgs model coupled to a decoupled qubit via this coupling.
for spin 1/2, you don't need to add an extra cube. Like on the left-hand side, you already have. a key.
No, you do need to couple to a qubit. But the claim is that, so that's one description of this, the dual of the spin 1/2 impurity. But what we're claiming is that there's a different description, which is that it is the pi flux vortex line. So if you'd like, you can alternatively state that spin flux duality is an IR duality between this spin impurity in the abelian Higgs model and the pi flux vortex line. Incidentally, there's a kind of corresponding, so there's two ways to define defects, at least. One is kind of like as either disorder operators or like using the fundamental fields of the Lagrangian. Another is by coupling in new degrees of freedom. So this here we've described both of those ways on the abelian Higgs side. This way kind of is using new degrees of freedom that we add in on a line. This way is kind of like by not doing that, by just defining a disorder operator. You can ask, on the O2 side, we only defined it one way. We defined it as a by adding in new degrees of freedom. Is there like a way that only uses the fundamental fields of the Lagrangian? And the answer is yes. There's this kind of Wilson line description, which says that it's the trace of the path ordered exponential of where here these are T plus, Tx, Ty, Tz are matrices representing SU2 in the spin S representation. So if you like, this is like a description that doesn't add new degrees of freedom. So there's both on both sides.
But do you get that trace by like literally doing the path integral of Z's?
Yeah,
So these are like literally the same operator, maybe, after you integrate out the auxiliary degrees of freedom.
Yeah, I think, after you integrate out the Z's, you basically just get this.
But you can do that for higher S as well, right?
You can do this for IAS, yeah.
So it's not specialized plus 1/2. Just
No. That's right. Yeah, so okay, good. So you could ask like, is there a description like the vortex line for higher S? And I don't.
I mean, something do I guess in the abelian Higgs side, you take the vortex and you dress it with a Wilson line of both fold, right? I don't know if that
that's
interesting.
interesting.
I mean, you also get an infinite family there because you can take any charge.
You get like twice as many because this is only for positive integer S, but
I see.
But I don't know. No, maybe there's some. Yeah, no, it's very. Yeah, I hadn't thought about that.
Any other questions? Let's thank Brandon.